So this is the polar form of complex numbers, and I need you to recall that Z is a complex number that has a real and imaginary part, A plus BI, and it can be written in the form R, comma theta. That's the polar form. Also, we've seen that as cis notation, and some of you are complaining, so I'm going to try and stick with cis. R is the modulus of the complex number, and theta is called the argument, and it is the angle from the positive x-axis in an anti-clockwise direction, which you'll know is that's how we do everything in maths except for bearings. But we don't have to worry too much about bearings at the moment. So this is called the Cartesian form, coordinate form. It's written, it can be represented on here like a coordinate, A and B. And then polar form is represented as a distance and a direction. The direction denoted by the angle theta, the argument, and then R is the modulus, and that's the distance from the origin, or from the starting point of the vector, whatever that is. And there we go, length and directions. It's sometimes also called modulus or argument form. And you might be asked, and I think I've got an example of this later on, you might be given a complex number, Z, and asked to determine the argument of Z. Not Z in polar form, just the argument. And so if you can just find that, that's important as well. If theta or R are known, so if theta and you can go from polar form back to Cartesian form through our cis notation. So that is, we just substitute our theta and R into this cis notation here, and it'll, cos of theta will be able to be determined. Multiplied by that will give you an imaginary part and a real part there, but you also get the idea from here as well. So both ways, actually converting from Cartesian form to polar form is slightly harder than conversion the other way back. So here's a quick example. I want to write W equals negative 4 plus 3i in polar form, and I might need you to help me on your calculators perhaps. So for question A, I need to determine R and I need to determine theta. The modulus, so R is equal to the square root of negative 4 squared plus 3 squared. And I've chosen those numbers to work nicely for R, but they don't work nicely for theta. In this case, you get a 3-4 triangle. So I get the square root of 25, which is 5. We'd normally say it's plus or minus 5, but in this case we say 5 because we're talking a direction. So it's a modulus. Modulus is positive. Theta, we typically write as tan inverse of B over A. But I would encourage you, so I'm just going to put this down as 3 over negative 4. We have to be quadrant aware. So as you saw, we can set rules up. This works for vectors as well, where we say, do this, step, 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 and it will give you the exact angle. But questions change and they vary, and I want you to be able to be quadrant aware just through logic and common sense. And so the one way that you can do this is to just quickly draw where this complex number is. It doesn't have to be a neat sketch. It doesn't ask you to sketch it. But if I go negative 4, 3, it's there. It's therefore in the second quadrant, I'm expecting my angle theta to be somewhere between 90 degrees and 180 degrees. So somewhere between pi on 2 and pi. That's my expectation. I don't know what my calculator is going to feed back to me, because tan inverse of negative 3/4, tan is negative in the fourth quadrant and the second quadrant. And I suspect my calculator will give me a fourth quadrant answer. Remember, tan is just pi rotations around the circle. So it's really easy to get to the other quadrant answer just by adding pi or subtracting pi as you need to. Has anybody done that for me, by the way? Know that bit in a calculator? Say it again, sir. Negative 36.87, so we're working in degrees. That is here. I don't want it to be there, so can you add 180 to that for me, Harvey? $126. Okay. 143.13 is the angle around here. That's our argument. We've ensured it's in the right quadrant. That's the hardest thing to do, and the most common mistake is to make sure it's in the right quadrant. Are there any questions on that? So just keep that in mind with tan. The reason why tan's so nice, because you could do it with sine of, but like this triangle that's formed here has 4 and 3. So you could, and you also know the modulus now is 5. So you could easily use sine or cos. But the good thing about tan is sine and cos are positive and negative in random quadrants, and you've got to take away from 360 or add, subtract from 180, stuff like that. With tan, it's just a 180-degree add-on every time. So it works really nicely. Right, 7, 38 degrees in Cartesian form. So for this, I'm going to use my cis notation, and I'm going to say r cis theta is equal to 7 cis 38, and I'll need your help again. That's 7 cos 38 is the real component, plus 7 sine 38 I. And I don't know what that is. It's going to be not nice. .07. Is that the cos? Oh, that's on. Plus 2.07 I. Oh. .69 plus 2.07 I. Okay, 38 degrees is in the first quadrant, so I'm expecting them both to be positive, and they are. Any questions on that?
Yeah, that's
What's in radian?
his calculator's in radian.
Oh.
Yeah, so it's wrong for like.
But it says non-real.
Oh, right. So 5.52 and 4.31.
Okay, you have one job. There we go.
Are you sure, Mommy?
Yes.
Oh.
Yeah, I think that was all reason for that.
Is that in the
Okay. So that's as easy as going from there to there for polar into Cartesian form. Hopefully we're happy with that. Very quickly, if z equals 3 plus 7i, what is the value of z bar in polar form? We talked about z bar, that's the modulus, so that's the conjugate of z. What is the value of any z bar where z is r cis or r cis theta in polar form? I'm going to just stop this for a second and give you a minute to think about it. So the answer we've got is not for this particular one, but generally for z bar. This is now not working. Generally, for z bar, where z is equal to r cis theta, we have a general solution where we put our coordinate here. This is a plus bi. The conjugate of a plus bi is here. That's a minus bi. And so we get a modulus that's the same, and we get an argument that's flipped over the x-axis. So we go from having theta to having negative theta. And the only time this is a problem is if we started with a minus b, but that was written as an angle between 180 and 270. If you flip that over, it might go out of domain. So you've got to be a little bit careful of that. And I'll show you that over here. Let's imagine we had this one, and it's there, and we'll say that this is pi on 6, and so this is pi plus pi on 6 is 7 pi on 6, and that's our value there. It's r, so our complex number is r cis 7 pi on 6, and if we flip that, z bar is equal to r cis negative 7 pi on 6, but this is probably out of our usual domain. We've flipped it and we're treating as the angle in the negative, back around to here. If we add 360 to that, that will spin it right the way around, which is 2 pi, and it will give us something that's a little bit more reasonable or suitable within a domain, and that's 5 pi on 6. So all we do is we add 2 pi to the angle, the argument, to get it around to something that's more sensible if we got into a heavy negative one. That's the only problem you've got to deal with. But ultimately, if z equals r cis theta, then z bar, or the conjugate of z, is r cis negative theta, and we just make sure we deal with the argument being too heavily negative. And of course, we would see that if we did the calculation here, and I'm probably not going to do it to be honest because I've seen it, but z is equal to 3 plus 7i, which is equal to something. We could determine r cis theta, and if we did z bar is equal to 3 minus 7I, we would get cis negative theta. In all likeliness, we get something else, but when we subtracted 2 pi, we get r cis negative. You can play with that if you want to. There's examples in the textbook to play with, but that's the idea behind it. Some quick operations, and then I'm going to dump it at the end of example 4 and leave you alone. So operations on complex numbers in polar form, adding and subtracting. We'll do this one really quickly in a second, but if we're adding and subtracting in polar form, it's basically impossible to do without going back to Cartesian form. So Cartesian form is great for adding and subtracting. Polar form turns out to be really good for multiplying and dividing, much better than Cartesian form. So I would write this back as 2 cos pi on 3. I'm going to zoom in here. 2 cos pi on 3, let me make that look like a 3, plus I times 2 sine pi on 3 there, and then plus cos 2 pi on 3 plus I times 5 sine 2 pi on 3. So cos of 60 is a half, and 2 times a half is 1, so it's 1 plus 2 times root 3 on 2 is just root 3, 1 plus root 3I, and then cos of 2 pi on 3, cos is negative in the second quadrant, so cos of 2 pi on 3 is the same as negative cos of pi on 3, and that becomes negative 5 on 2, and then sine of 2 pi on 3, sine's positive in the second quadrant, so it's the same as sine of pi on 3, and that becomes plus 5 root 3 on 2i. We get those two in Cartesian form, and then we just add the real and imaginary parts, and it gives us negative 3 on 2, and then root 3 plus 5 on 2 root 3 is equal to 7 root 3 on 2. You can do the maths there if you need to. And that's our answer. Now, the only thing you have to be aware of is that once you've got this answer, you may be required to go back into polar form. So we might have to take that time to say, okay, and r is equal to the square root of negative 3 on 2 squared plus 7 root 3 on 2 squared. And if you've got a calculator, hopefully somebody's working that out for me now. And theta is equal to tan inverse of 7 root 3 on 2 divided by negative 3 on 2. And that's equal to tan inverse, I'm just going to simplify this, of negative 7 root 3 on 3. I believe Harvey's on it, and Ozani's on it. We've got either of them. Which one? R is equal to the square root of what? 39. Okay, cool. Negative 76.1 degrees. And of course, we have to go back and be quadrant aware. And in this case, I've got a negative horizontal value and a positive vertical value. And so if I do a little sketch of where this is, it sits approximately negative and positive about here. So it's in the second quadrant. So I have to add 80 to that. And that gives me, so this is in quadrant 4, but it's actually at 103.9 degrees in quadrant 2. And so our solution is root 39 cis 103.9. We have broken the rules a little bit and gone into degrees here, where the question is clearly in radians. So just be careful of that. We probably should go back to radians. But as you can see, the relationship between this and this, there's no connection. When we're adding, it just doesn't work. So when we do this adding, we probably have to go back out to cis notation. Unless you get lucky and it's something where the arguments are the same, then you might be able to simplify it a bit easier. Multiplication by a scalar. I haven't even got an example of this because it's pretty easy. If you multiply by just a number, it just does that. You just multiply the number by the modulus. And standard multiplication happens a little bit like as we talked about with de Moivre's theorem. And we'll get back to next lesson. But we multiply Z1 and Z2 in these polar forms, we just multiply the two moduluses and we add the arguments. If we divide, then we divide the two moduluses and subtract the arguments. That's how that happens. And so example 4, which we can do quite quickly and then talk about the geometric interpretations, we get A WZ is equal to 3 times 5 cis pi on 4 plus pi on 5. What's pi on 4 plus pi on 5? Excellent, thank you. So 15 cis 9 pi on 20. And whatever that is. And then B, the division, we get W on Z is equal to 3 over 5 cis pi on 4 minus pi on 5. And that, of course, is equal to 3/5 cis pi on 20. Geometrically, and this is probably going to be pretty hard to see, but maybe we need to play around with this a little bit later. But pi on 4 is 45 degrees. So W is here. So it's got a length of 3. Probably should scale that down a bit, shouldn't I? In fact, they're all in that first quadrant. So let's do this. Scale this out. W is out on a length of 45, an angle of 45 degrees. And it's got a length of 3. Z is out on a slightly smaller angle, pi on 5. Pi on 5 is 36 degrees, but it's longer. So Z's out here, and it's got a length of 5. And WZ, 9 pi on 20. What's 9/20 of 180? I'll give you a hint. It's 81, good. Don't need to give you a hint. 81's up here. And it's also got that modulus of 15, so it's right up here. This is WZ. It's got a modulus of 15. But you'll notice here with WZ that we're adding the argument. So this is just rotated around. It's W rotated around by Z's argument. Because we're adding the argument, there are geometrical implications here. We'll get those two arguments and add them. If you had one here and we added the arguments, it would be on the x-axis. So we're adding the argument, which then creates that just rotation factor. Because of De Moivre's theorem and because of that basic multiplication in polar form, it creates a rotation, but it also blows out the modulus. And of course, W over Z is 3/5, so it's this little green line here, and that angle is 1/20 of 180, which is 9 degrees, or pi on 180. So this, well, not 18 or 180, 20. This angle here is the same angle as that gap between the blue and the purple. That's what division, that's the implications of division. So there are some geometrical implications that might come up again as well as an interpretation thing, but the implications are pretty easy and you can work through those if you need to. Right, I'm leaving it there. So thank you for your patience.